Yeah, I'm Andrew Mills, a research scientist in the Electricity Markets and Policy Department at the Lawrence Berkeley Lab. And today I'm going to talk about the potential roles for storage in integrating variable renewable resources and the emerging commercial interest in hybrid renewable plants. The goal is to share some of the insights from our research that can inform discussions about use cases for storage and some important factors to consider. Next slide. I'll first talk about integration, and this section will primarily focus on the challenges of integrating variable renewable resources into the grid. Next slide. The integration challenges include the variability of resources and their contribution to resource adequacy. Variability is associated with the changes in the supply within the operating hour over multiple hour events. And uncertainty is due to forecast errors in the day ahead and also closer to real time. The consequence of the variability and uncertainty is that the actual supply of generation will deviate from what was scheduled. And covering these deviations can require flexible resources to quickly respond, or it might require system operators to hold resources in reserve to cover those deviations. The fact that generation from variable resources is not aligned with the times of greatest need can lead to lower contribution towards meeting resource adequacy requirements. An experience with high penetrations of solar in California shows how the timing of greatest risk of outages can shift from the hot summer afternoon into the early evening after the sun sets. This variability and uncertainty is inherently part of the power systems, though, due to varying load. It's just that variable renewables increase this variability and uncertainty, and managing it can impose additional costs. Over the past 2 decades, numerous studies have been conducted across the US and internationally to understand the integration costs of wind and solar. The resulting integration costs across these different studies vary for a number of reasons, including the mix of resources that's in the region, whether these costs arise for utility, it's also its own balancing authority, or versus it's part of an integrated, coordinated regional system, and then also just how the study defines and calculates the integration costs. Most of the wind integration cost studies find that these costs associated with managing the variability and uncertainty of wind are below about $5 a megawatt hour, with the exception of some small utilities in the West, their own balancing authority in the West. And these costs don't necessarily appear to dramatically increase with increasing penetration levels. We see a smaller number of studies shown here on this slide that have estimated the integration costs for solar, and they show that the general range of costs are somewhat similar to what I reported for wind. The study that's marked here as APS Argonne 2013 in this chart was based off of a study that involved researchers from the Argonne National Lab, Berkeley Lab, and NREL. And I'll talk a little bit more about the results from that particular study coming up. Next slide. It's clear that solar plants see dramatic variability due to passing clouds, and that this cloud cover can be particularly hard to predict. The red lines shown in this chart show the output from 32 different simulated PV plants on a relatively clear day, and then on a partly cloudy day. And you can see that at one of these individual sites, the production of solar can drop off dramatically within minutes at these particular sites. So the study that we did focused on strategies and costs for managing this solar at the level of the full balancing authority. The resulting output from those same 32 plants was smooth when aggregated across all of the plants that were in that utility footprint. And that's what's shown in the black lines there. In particular, that rapid drop-off in production that we would see at a single plant didn't appear at all in this aggregate profile, even on that partly cloudy day. And so as a result, the cost of the incremental reserves that would be required to manage this additional variability and uncertainty at that aggregate level were below about $5 a megawatt hour. Next slide. Alternatively, we recently evaluated an often discussed strategy of trying to smooth the PV ramps at an individual plant using storage. And here you can see how we simulated the operation of that battery, and we used it to limit the ramps from that individual PV plant. On a partly cloudy day, that battery is rapidly charged and discharged to limit the aggregate ramp of the PV and battery system to about 5% of the PV capacity per minute. In this case, we sized the battery power rating similar to the PV plant, but that the amount of energy that the battery needed to store was relatively small. So at full power, this battery could be fully discharged in just 15 minutes. Next slide. We then used some modeling tools that are available from NREL to estimate the incremental increase in the cost of a PV system due to the additional battery equipment needed to provide this ramp control. The more stringent that ramp rate limit was, the more energy that battery had to be able to store, and it increased its initial costs. The costs also increased with this more stringent ramp rate because the batteries had to be cycled much more often. And cycling the batteries can be costly since each cycle can degrade the battery and force its early retirement. So based off of these two utilities in Florida that we were looking at, the additional cost of this ramp smoothing ranged from about $10 to about $40 a megawatt hour, depending on the degree of smoothing that we imposed. Another interesting finding that we saw was that the costs were smaller for this small 75 kilowatt PV system, which used data from the city of Tallahassee, compared to the costs from this larger 12.5 megawatt system that was from the utility in Jacksonville. And presumably this lower cost for the utility in Jacksonville is because there's some ramp smoothing that can happen even within the footprint of that single plant. And so that meant that smoothing that happened within the footprint led to some lower variability that the battery then had to manage, and the fewer battery cycles overall, and that extended the battery life and ended up with this somewhat lower cost. So the main takeaway from this analysis was that in comparison to those earlier integration cost studies that I mentioned, it is possible to smooth out the output of the individual plant with storage, but it can sometimes be easier and more cost effective to try to manage that aggregate variability and balancing at the authority level. Next slide. So now I'll turn to another issue that's related to integration, and that's this lower contribution of variable renewables to meeting resource adequacy targets. The contribution of variable renewable resources to resource adequacy depends on the production during those times where there's the highest risk of insufficient generation to meet demand. When you have low penetrations of wind and solar, the periods of highest risk of outages is often in the mid-afternoon on a peak summer day. And this is showing data here from the Mid-Continent Independent System Operator. The chart on the left shows that at these low renewable penetration levels, the solar production, shown in the yellow lines here, is relatively high during the times of the highest risk of outages, which is shown down below by these sort of blue triangles at the bottom. The higher those blue triangles are, the higher the risk of outages. Wind, on the other hand, it tends to produce less in the middle of the day during those periods of high risk than it does at night, which is shown in the green lines there. So as a result, the contribution of solar towards meeting resource adequacy targets, which is shown here on the right, it's about 60% of the nameplate capacity of solar when it's at low penetration, while the wind is at just about 20% of its nameplate contribution. This contribution to resource adequacy as a percentage of its nameplate is often called the capacity credit of a resource. And one of the most widely accepted ways to calculate it is using a probabilistic model that calculates what's called the effective load carrying capability, or ELCC. And we see that with increasing shares of renewables, this period of high risk of outages can shift away from this traditional afternoon period and shift into the early evening after sunset. What happens is that because of this shift of the timing of risk, that can lead to a steep drop-off in the resource adequacy contribution of adding more solar and a somewhat more modest reduction in the capacity credit of wind. Next slide. So some of the research that we were doing, we wanted to evaluate what role storage could play in helping to increase this capacity credit of solar by evaluating different configurations of solar and storage. We could have the system be completely independent from one another. That's where we start off at the top here, where both are just independent and connect to the grid and don't really interact with each other directly. Alternatively, we could sort of bring them together with some sort of shared infrastructure. It could be a shared inverter, or it could be some limited point of interconnection that they share. And this loosely coupled configuration has those behind this shared inverter, but still allows the storage to charge from the grid or to charge from the solar. On the other hand, this tightly coupled configuration, it restricts the storage to only charging from the solar. And our question again was, what is the resource adequacy contribution of these different parts, and how does that change as we couple them with these different configurations? Next slide. In order to try to address these questions, we first needed to develop a way to dispatch the storage in order to maximize its capacity credit. So we started with an approach from NREL that approximates the capacity credit as the reduction in the net load during the top 100 net load hours. On our side, we then developed a simple and fast algorithm that could dispatch the storage to maximize its peak net load reduction. And in particular, what we're trying to do is basically minimize the area of this purple area here and the chart on the right in order to maximize its capacity credit as shown by the pink area. Next slide. So we evaluated this simple approach that we developed by comparing the results based off of our method to results from a method that's used in practice by a Western utility. So for that utility, they used this more detailed probabilistic model to calculate the effective load carrying capability of storage, which is shown by the dashed lines. What we did is we sent them over our code, and they ran that same load and solar data from their analysis through our code, and then returned the results, which are shown in the solid lines. We did this for different levels of 4-hour duration storage, for different levels of deployment of that, in scenarios that had different levels of solar. So there was a low solar case and a high solar case. And as you can see from this chart, both approaches show that the capacity credit of 4-hour storage starts somewhere close to 100% of its nameplate capacity, but then it starts to decline as you add more and more of that storage. And the reason for this decline now is that remaining net load peak that has to be met by the storage, as you start to clip off kind of the narrow peaks of that, it just starts to get wider and wider. And that means that continuing to reduce the peak net load requires longer and longer duration storage. Or if you just had 4-hour duration, you sort of get a lower and lower effective capacity credit from it. One of the things that's interesting about this is that when you have this high solar scenario, though, that high solar can narrow that net peak load, and that can actually make the 4-hour storage slightly more effective. So that's why the blue line is with low solar ends up being below the red line with high solar. But again, we still see the same sort of behavior with increasing penetration levels where that capacity credit can decline. So for the most part, what we took away from this was that our simple approximation method was validated using the data from this Western utility. So we then go ahead and take this approach and we apply it to the solar and storage cases for utilities in Florida. Next slide. So we were, again, particularly interested in trying to assess the capacity credit of these different solar and storage configurations. And we were working with a number of municipal utilities in Florida. So we're showing results here for 2 different utilities. And what we find to begin with is that the capacity credit of storage depends on its duration. For the storage to get that full close to 100% capacity credit that we're seeing earlier, it does require something like 4 to 5 hours of duration. And the capacity credit of just the storage alone is shown by these blue lines for different levels of storage duration. On the other hand, if we had storage and solar combined, and we did this in this independent way, we'd get this red line here, which is just simply the sum of the capacity credit of the solar in this region, which was about 50% of its nameplate capacity, to the capacity credit of storage. And that, again, that capacity credit of storage starts to increase as we increase the duration. We saw that for these other coupled cases that it showed somewhat of a similar behavior, except for at the point where we start kind of running into the limits from this shared infrastructure. And again, you could think of that as something like a shared inverter or a point of interconnection that limits the total capacity. And so those 2 lines are shown by the purple and green lines here, where we had that loosely coupled and tightly coupled. One of the interesting findings was that for a utility that peaks both in the winter and in the summer, that's more the case for this Jacksonville utility, there can be times where further restricting the storage to only charge from the available solar could further limit its capacity contribution. And so what happens is that there's some cold weather events that come by, and the solar might be insufficient to charge up the storage in order to kind of continue to achieve that capacity credit. So in these rare instances, we actually ended up with a somewhat lower capacity credit of the solar and storage when it was forced to only charge from the solar, whereas if it could charge from the grid, there was some available power in order to do that. But again, these differences were somewhat minor and only limited to that case where we saw the high summer and winter peaks. But overall, the message from this was that the storage can contribute to resource adequacy, though the specific contribution of it is going to depend on the configuration. Next slide. So for the last part of this presentation, I'm going to turn to describing commercial activity for these combined renewable energy and storage plants and some of the broader motivations for their deployment. Next slide. So the overall motivations for hybrid plants extends beyond just the narrow issues that we've looked at so far. But one of the important motivators is the investment tax credit. And right now, storage capital costs can be reduced by this investment tax credit as long as that storage is charged from a renewable resource. The standalone storage, on the other hand, isn't eligible right now for that same incentive. There's also potential cost reductions that come from shared permitting, shared interconnection, and other equipment costs. And when a solar and storage plant share an inverter, it's also possible to capture some of this otherwise clipped energy and sort of increase the overall output of the solar plant. On the other hand, you might see that by siting the storage with the renewable generator, you might forego some opportunity to site that storage closer to loads. And because of some of these constraints, it might actually limit some of the operational flexibility of the storage if it's sited with a renewable generator versus somewhere else. And then finally, there's some regulatory uncertainty, which is some of the rules on interconnection and participating in wholesale power markets continue to evolve. Next slide. But what's clear is that the commercial interest in hybrids is growing. In the next few slides, I'll just show some of the data that we have indicating that this growing interest, and it's all based off of what we're seeing in interconnection queues. The interconnection queues across the country are dominated by wind and solar right now, with growing interest in storage, both in this sort of standalone configuration and co-located or hybridized with wind and solar plants, which is shown by the hatched portion shows the amount of wind and solar that's going to be paired with storage. And not all of this that's in the interconnection queues will be built, but it does give you some sort of sense of what's in the development pipeline and where commercial interests lie. Next slide. What we see is that the bulk of this hybrid activity in solar is primarily for solar and storage, and most of that's happening in the Western US. About 2/3 of the solar that's in the CAISO queue has storage in it, and half of the solar in the West also has storage with it. We see wind hybridization is also increasing, and that the total amount of wind hybridization is less than what we see for solar, but it's highest in the California ISO, where about half of the wind that's in the queue has storage with it, and that's sort of less than about 7% of the wind has storage with it in all the other regions of the US. Next slide. So this slide just shows some of the data that summarizes some of the cost data that we're collecting for a small subset of projects that have signed power purchase agreements. And one clear trend that you can see in this is that the costs of solar and storage hybrids are declining. And we've seen projects in the Southwest that have signed agreements for as low as $20 to $30 per megawatt hour. You see the projects in Hawaii are more expensive, but they're also following a downward trend in the costs. And for a limited set of the projects in here, we've used this to try to estimate the incremental cost of the battery. And we see that a 4-hour duration battery that's sized to about 50% of the PV nameplate capacity, it increases the cost of the PV and storage plant relative to just a PV plant by about $10 per megawatt hour. Next slide. So we also then used some historical wholesale market prices to estimate the additional market value of adding storage to a solar and wind plant. So rather than dedicate the battery to doing smoothing of the output or to only providing resource adequacy, in this analysis, we're dispatching the battery to maximize the overall revenue of the battery, subject to constraints on limiting the point of interconnection capacity and also restricting the battery to only charge from the renewable generator. And what we find is that the addition of the battery can increase the value of a wind and solar plant in a sort of a similar way, and significantly more than what we saw in Texas, where in this case, this analysis is using data that's just covering a period of 2016 to 2018. And the reason, in part, that we saw this higher value in California was because of this potential increase in capacity value. So we're seeing it in California that 4-hour storage gets 100% capacity credit. And then you also have some higher volatility of prices in California during this period of 2016 to 2018. I'll note that in more recent work, we've extended that to cover through 2019, where we did see some higher volatility because of some high peak load times. And you do see that Texas sort of jumps up, where you can see a similar adder in the value of adding storage to a PV plant and wind plant in Texas because of that higher volatility in 2019. But again, if we just kind of focus on what we saw in California, if we take the additional value that we got from adding the battery here, and we compare that to that earlier cost that we mentioned of about $10 per megawatt hour for additional costs, you can see that it does look quite attractive with its historical data in California, but less so in Texas, except for when you start to bring in these particular high-priced years. Next slide. So another way to look at this same situation is to compare the value of the standalone renewable generator and the standalone battery to the value of the solar or the generator and storage integrated into a hybrid plant. And here, in this case, we see that the hybrid had a slightly lower value because of the two constraints that we imposed. First was there was an assumption that the hybrid storage could only charge from the renewable generator. And second, there was an assumption that the hybrid would have a single point of interconnection and the capacity was equivalent to the generator capacity. So those two constraints somewhat lower our value, and you'd have to compare any cost advantages you'd get to siting those solar and storage together to see if the advantages of hybridizing from cost perspective outweigh the potential decrease in value from these additional constraints that are imposed. Okay, next slide. So just to wrap it up, I have a few questions here that states might ask utilities that are beginning to bring in storage and hybrids into their planning discussions. First one is just to think about how is it that utility is able to take advantage of geographic diversity to manage these challenges with variability and uncertainty. And for the most part, the important takeaway is that we saw that the variability at a plant level can be much greater than the variability over the footprint of a utility. Then managing this aggregate output requires fewer resources and can be much less costly. Another question is just how much storage is needed to manage the aggregate variability and uncertainty compared to managing it at each individual plant? And how does your resource adequacy assessment account for potential changes in the contribution of resources with increased deployment? Another one is, how do the costs and benefits of hybrid configurations compare to those standalone configurations? We saw that was important. And what potential cost or value synergies of hybrids do you account for in planning and procurement? And finally, just what are the consequences of allowing or preventing grid charging from hybrids? Does grid charging affect the eligibility for state policies such as renewable portfolio standards or clean energy standards? And then so there's also a poll here that's on your screen now, which is just to ask for which of these models of storage deployment is likely to be or is most used in your state right now. And the three options are, it could be as a standalone front of the meter asset, as a behind the meter asset, or hybrid with a co-located generator. It seems like the results here is that for the most part, a lot of the responses are following what we're seeing with the commercial interests, in that the interest is primarily around co-locating it with the generator in a hybrid configuration, and that you see some of it as the standalone in front of the meter and quite a bit less as a behind the meter asset. Interesting. Okay, great.